All right, in this problem we have a student who wishes to use a spring to accelerate a cart along the horizontal level track. This is the image given. They tell us that the spring is attached to the left end of the track as shown and produces a nonlinear restoring force of magnitude. Go ahead and write this down. F spring is equal to AS squared plus B times S, where S is the distance the spring is compressed in meters. A measuring tape marked in centimeters is attached to the side of the track. The student places 5 photo gates on the track at the location shown. So part A, we want to derive an expression for the potential energy U as a function of the compression S. So we're basically trying to derive the spring potential energy here, and we're going to do that the same way that we did in class, where we have spring potential is equal to the negative of work done by a spring, which is equal to the negative integral of the force of a spring dotted with, in this case, it's ds for the distance. Okay, now one thing to note is that it's a restoring force, and so the dot product here, so it's a restoring force, so the magnitude of the force is negative. So just like with a with Hooke's law, the spring force for Hooke's law is negative kx. Okay, here it's a restoring force, so it's going to be negative everything they gave us, but they just gave us the magnitude. Okay, so if I go ahead and plug that force in, then we're going to end up with U from the spring is equal to, we have 2 negatives if I do that, so we'll just have integral of AS squared plus BS ds. And our integral needs some limits here, and we're going to go from S is equal to 0 to some point S, however far we compress it. Okay, and then the spring force, the integral for this is equal to integral of AS squared is going to be 1/3 AS cubed plus the integral of BS is 1/2 BS squared. Then we evaluate that from 0 up to S, and then we're going to end up with U for the spring is a 1/3 AS cubed plus 1/2 BS squared. And that's it for part A. So now in a preliminary experiment, the student pushes the cart of mass 0.3 kilogram into the spring, compresses the spring 0.040 meter. For this spring, A is 200 Newton per meter squared, B is 150 Newton per meter. The cart is released from rest. Assume friction and air resistance are negligible only during the short time interval when the spring is accelerating the cart. So for part B, we want to first find the speed immediately after it loses contact with the spring. So if we compress the spring a distance of 0.4 meter, then, so we're going to compress this 0.04 meter, okay? So this would be the equilibrium point. When we let go of the spring is going to be pushing the cart past its equilibrium to a distance of 0.04 meter on that side. And so therefore the cart is going to lose contact with the spring at S equals 0.04 meter. So then if we plug in some numbers into our, actually we need to find a relationship for speed for this. So for part BI, we'll start out with conservation of energy. So we're starting out with all potential. So that is our initial energy equals final energy. and all of our final energy will be kinetic final. So we have spring potential is going to be equal to the equation we just found, and we're going to plug in 0.04 meter for it. So we'll have 1/3 AS cubed plus 1/2 BS squared is equal to a 1/2 MV squared, and then we can solve for V here. So we get V squared is equal to 2 over M times all of this, 1/3 AS cubed plus 1/2 BS squared. And then we're just going to square root the value to get V. So we're going to end up with V is equal to, if you go ahead and plug your numbers in here, you should end up with a value for speed equal to 0.91 meter per second. So here you're plugging in A is 200, B is 150, S is 0.04, and M is 0.3. All right. Next, we want the impulse given to the cart by the spring for part 2. Impulse equals integral of force with respect to time. And we don't really know anything about time, but we can set this equal to the change in momentum. So impulse equals change in momentum, where change in momentum is the mass times the change in velocity. And if I plug numbers in here, this is going to be 0.3 kilogram for the mass, and then times that by the velocity we just found, 0.91 meter per second. And we'll end up with a change in momentum. If you plug that into your calculator, you should get 0.273 kilogram meter per second, but we'll leave it as 0.27. All right, and that's it for part 2 of part B. So now it says, in a second experiment, the student collects data using the photo gates. Each photo gate measures the speed of the cart as it passes through the gate. The student calculates a spring compression that should give the cart a speed of 0.320 meter per second. After the cart loses contact with the spring, the student runs the experiment by pushing the cart into the spring, compresses the spring, the calculated distance, and releases the cart. So the speeds are measured with precision of 0.002 meter per second. Positions are measured precision of 0.005 meter. So here's the data given, and then for part C, we want to graph the speed of the cart as a function of position. So we want speed over here in meter per second, and we want position on the horizontal. Units are meter. All right, so looking at the position data, that's pretty nice. They have everything in increments of 0.2, so we can just copy that. 0.20, 0.40, 0.6, 0.8, all the way up to 1. And then for the speed, we go from 0.412 to 0.407, 0.399, 0.374, 0.338. So that's kind of a little bit weird for this graph. So what I would actually do is start the graph at 0.300 right here, and then go up by 0.05s. So this value would be 0.400, and then this would be 0.500. All right, so now we just graph that data. So at 0.2, we are at 0.412, so about there. So each one is worth 0.01, each small increment. At 0.4, we're at 0.407, so it'd be about there. At 0.6, we're at almost 0.4, 0.399. At 0.8, we're at 0.374, so 0.35674. And then at 1, we are at 0.338. So we'll go 1.388 is about there. So there's our graph. So now we want to compare the speed of the cart measured by the photogate 1 to predict the value of the speed of the cart just after it loses contact with the spring. List a physical source of error that could account for the difference. So velocity measured by photogate 1. This is part C. What part is this? Part CI. So graphing it was just part C, and then part CI. Comparing the velocity at photogate 1, which is equal to, from the data, it's equal to 0.412 meter per second. So this is the measured value. And then they give us a value earlier in the description. They say that the predicted value is 0.32. So V equals 0.320. This is the predicted value. So we'll put an M next to this one and a P next to that one so we know one's measured and one's predicted. So the question is, compare the speed and then list a physical source of error that could account for the difference. So clearly the measured value is greater than the predicted value. And so why is that the case? So there's a few different reasons why. I'll give you one of them. So one reason could be the model given or the equation given. So in the equation the equation we used to find velocity, we had to rely on the potential energy that we found, which came from the force given. And so maybe one source of error is that these values, A and B, in our equation could be wrong. So they could be too small. So we could say the equation used to predict the speed could have values that are too small. Right? So A and B should be larger. That's one source of error. So think of some other ways that could cause that source. Why? So think physically. Why could the speed measured be greater than what we predicted? What are some physical reasons for that? All right, so now it says, from the measured speed value of the cart as it rolls down the track, give a physical explanation for any trend you observe. So there is sort of a trend here, and if I draw that out, you can see that the velocity seems to be decreasing at some rate. And so why is that the case? So for part 2, we can see that the velocity decreases after it leaves the spring. So it's nothing to do with the spring here. Velocity decreases. And this is possibly due to friction, right? Friction in the wheels of the cart. Okay, it could also be, another source could be the cart is uneven. So maybe the track goes uphill a little bit. So we could say the track could also have an incline. And so it looks like that's it for this problem. Again, go ahead and take a minute and see if you can't figure out some other sources of error for part 1.